Hello guys, welcome back to the channel. My name is Desmond. In this video we will talk about basic input-output in assembly language, and we would also talk about how to program the 7-segment display. So once again, before we move forward, I need you to understand all the labs in lab 0, 1, 2, 4 and 5. So lab 3 knowledge is good to have, and you should also know how to connect a circuit based on the schematic diagram, because we won't be showing the breadboard connection. You should also need to understand the AND logic operation. And what you could expect from this video is that first of all, we will be interacting with machines, because finally in this lab we can input something to the program, and we would receive an output signal from that MCU, the microcontroller unit, to the LED via a port. So let's move on to the first program. So in the first program, we will be showing basic I/O. So this is our program right here. As usual, we will try to understand the program first. So this can be ignored because this will be present in every line. We will first jump to the main marker over here, and then we will set port 1 to be 00000000, which means to set port 1 as the output port. And then we would also set the port 2 to 1111, 1111, which means to set port 2 as an input port. Now this is just a simple rules in assembly on setting port 1 and port 2 as the output port and input port. Right now let's move down here to the program and start. First of all, because we have set the port 2 as input port, we can now read port 2. So this code right here means to read port 2 into A. So now A equals to whatever port 2, whatever input the port 2 has. And then, so before we move on, I think it's useful to look at this program over here. So this over here is our port 2. So port 2 are connected to this 2 push button over here, and also this 8-bit switch input. Okay, so this port 2 is our input port, and then this port 1 is our output port. So port 1 are connected to four LEDs over here. So when we read input from port 2, we will get 1s and 0s based on the condition of this push button, and also the condition of this 8-bit input. But in this case we won't be using this, so let's cross them out first. So if you could see closely, this let's call this push button and push button. Alright, so this push button is connected to port 2.4, and this push button is connected to port 2.5. If we look over here at the program, so we say that port 2.4 is B1, which is button 1. So the one that connects to port 2.4, let's call it B1, and the another one that connects to 2.5, we call it B2. So when we read the port 2, we are actually reading the entire 8 bits. So we are reading the both of the push buttons at the same time. And then how do we access the exact input of that push button? So to access the exact input of the push button, we would use P2 dot something. So if we want to know the input at port 2 4th bit, then we would say P2 dot 4. So P2 dot 4, alright, P2 dot 4 is connected to button 1. So JNB over here means to jump if the bit is not set. Jump if bit not set. So set is 1, so it will check this P2.4 if it's 1. So if this P2.4 is not 1, then jump to where? Jump to B1. So let's assume that B1 P2.4 or the push button 1 is actually set or 1. So how do we know if it's set? So if this push button is not pushed down, that means the current can flow from the VCC. So this arrow here means VCC. The current can flow from the VCC through this resistor to P2.4. So if this is not pushed down, that means this P2.4 is set because it receives 1 from its input, or because it is connected to VCC. If this, let's say that B2, this B2 over here is connected, alright? So let's say that B2 is pushed down. So if B2 is pushed down, the current will not flow from VCC to the pot because there's an extra resistor over here. So this resistor over here is actually a pull-up resistor. Okay, so this would prevent the current flowing from VCC to this P2.5 when this B2 is connected, because when B2 is connected, because this B2 is actually connected to ground, so when B2 is connected, it will set this P2.5 to be 0, or in other words, not set. Alright, so let's say that B2 is not set, so P2.5 is not set. That means that this J and B will jump the program to B2 over here, right? So just now the program, when we check for this line, the B1 is set. So if it's set, it will move on to the next line, right? So now no jumping at all. But now when we check the P2.5, we came to understand that P2.5 is not set, so 0. So it will jump to B2. So basically this is checking if it's 0 or not. So if 0, then jump. If not 0, then continue to the next line. Okay, so now let's say that we have jumped over here. Because P2.5 is not set, we have jumped over here. Now we'll run the program starting from here. Okay, so it will move 05H into A. So 05H, is the is hexadecimal. So if we look over here, hexadecimal, 0 is 0000, and then 5 it's 0101. So 05 it's 0000 0101, which is shown over here. Okay, so basically we move this 0000 0101 into A, and we move A to port 1. So port 1, if you remember, it's our output port, so it was set 0000 0101. Okay, 0101. So it will set a P1.0 to 1. Okay, then set P1.1 to 0, P1.2 to 1, P1.3 to 0, and the other ports as 0, but we will just ignore because they are not connected to any component. So let's look back at here, right? So VCC is 1, and let's look at the first LED. So the first LED is connected to P1.0, which is 1. So 1 and 1, that means no current will flow through. So this LED will not light up. So now let's look at the second LED. So this is 1 because it's connected to VCC. Let's look at the other side. It's 0. So this light, this LED will light up because there's a potential difference and current will flow from VCC to the chip. Okay. Now let's look at this over here. This will not light up because it's 1 on both sides. And this is 1 and this is 0, so this will light up. So in this case, if B2 is pushed down, then this LED and this LED will light up, okay, and the other two will not light up. Now after that, after we move 05H to A and A to port 1, we will display off-on configuration over here at the LEDs. Now after this, we will jump back to start, which is over here. Okay, so we'll read the input again. So this line over here is reading from port 2. We'll read and check the input again. So now let's say that now B1 and B2 are not pushed down. Okay, so these two lines will just run and no jumping would occur, and we'll move on to this line over here. Okay, so the condition is that B1, both P2.4 and P2.5, and the buttons that connect to P2.4 and 2.5 are not pushed down. If they are not pushed down, we will move to this line over here, which set all to zeros. And then now A is equals to all zeros, and when we move A to port 1, so this would all be zeros. Okay, so this would all be zeros. If this is all zeros and all the LEDs and this side over here is connected to 1, then all LED will light up. So if no button is pushed, all LED will light up. Now let's say that now the button 1 that's connected to P2.5 is light up, and the button 2 is not pushed. Sorry, I mean the button that connects to P2.4 is pushed, and the button that connects to P2.5 is not pushed. So now the case is this is connected and this is not connected. Okay, so now because this is connected, it will set P2.4 to be 0 because now that it's connected to ground, and this is not connected, so it will be 1. Okay. In that case, we will jump because this line will trigger the jump, and we will jump over to B1. Okay. Now at B1, we would set this as 1010. So it will be 0000 1010. And then if that is set, that means that this LED will light up, this will not, this will light up, and this will not. Okay. After that, we will jump back to start and read the input again. So this program just keep looping and checking for the input of button 1 and button 2. And depending on the input, if both buttons are not pushed down, all LED will light up. And if button B1, which is connected to port 2.4, is pushed down, then this LED will light up. And one more case is that when B1 is not pushed down and B2 is pushed down, then this LED and this LED will light up. Okay. So that is what this program is doing. So it's basically reading the input from these two buttons and then decide to light up the LEDs based on the input. Okay. So now for your lab submission, you will be building the 4-bit up counter, right? So I won't be showing the code here, but I will at least guide you how to do it. So the requirement is that you will use one push button to start or stop the 4-bit up counter. So what is a 4-bit up counter? So a 4-bit up counter is a counter that counts from 0 until 15, because 4-bit can represent 16 numbers. So in this case, the 6 numbers is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the 16 numbers that we want to count. So you will count from 0, which is all LED will turn off. So let's assume that this is our LED. And then to represent the 1, we would use the last LED. So we would say that if this LED is light up, then it is actually representing 1. So it's just like binary. It's actually a binary system. So up until 15, if 4 LEDs light up, that means we are actually counting to 15 already. Okay. So the first step is that you will need to complete the 4-bit up counter. So remember to use the subroutine, delay subroutine from lab 4 and lab 5. If not, your program would run too fast and you will not even see it counting. And then how to display 0. In this case, I give you an example. If you want to display 0, if your circuit is connected like this, then you will have to set all here to 1. So these 4 LEDs are connected to 1 on both sides. So these 4 LEDs will not light up. If you want to show 1, then you will just put, a 0 at the end. So only this LED will light up and the others won't. And up until 15, where you set all here to be zeros. So for 15, 4 of this LED will light up. So you just try to complete the 4-bit up counter first before you move on to complete the push button. So for this submission, you will only need one push button, and when the push button, let's say that when the push button is pushed down, you will start counting. Okay, and when the push button is up, then you will stop counting. So in that case, you will need to check for, let's say, that your button is connected to port 2.4. You will just need to check for port 2.4, and then if port 2.4 is pushed down, you will jump to B1, and then B1 will be your program over here to count the up counter, which is something like this one. Okay, so that's the tips for you to build the 4-bit up counter. Now let's move on to 7-segment display. So the 7-segment display looks something like this. So it has 2 types, common anode and common anode. So the difference is over here, the ground. So common anode is connected to ground at this pin, and common anode is connected to VCC at this pin. So let's say that we are using common cathode for this experiment, and we would ignore this for now. So to display a number, let's say number 0, we would need to connect the A, B, C, D, E, and F to VCC or 1s, right? So we will need to connect A, B, C, D, E, and F to 1s. Then this would display a 0 for us. So we can see over here, this is a table. And if we want to display 1, only B and C needs to light up. So only B and C needs to be 1, and others are all zeros. So this will be the input that we are going to send to this 7-segment over here to display the numbers out. So you will need to complete all this. You could just refer to this diagram over here, and up until F. So for F, you need to light up A, F, G, and E. So A, E, F, and G. So only these 4 pins need to be 1, and others need to be 0. Okay, and then one more thing is that for B, you cannot put a capital letter B because it might look similar to the number 8. So in this case, when we are displaying B, we need to display a small letter B. Okay. So what's the outcome of this lab? So we would have this 8-bit input. So it's like an individual switch at every number. So we will only be using 4 pins over here because 4 binary numbers, 4-digit binary numbers is enough to represent 15 hex 15 numbers, right? So from 0 to F. Now if all of them are switched off, or if all of them give 0, then we would display 0 over here. Okay, and if one of the pin is set to 1, then we would display 1, and if this pin 3 is set to be 1 and others are 0, then we need to display number 2. So this is the binary input, and this should be our output. So besides from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we would also need to display A, B, C, D, E, F. Okay. So let's jump to the program to see how to do that. So we can skip this line again. So first of all, we will move all zeros to A, this step, and then set A to P1. So this step will set port 1 as output port, and when we move all 1s to port 2, then this will set port 2 as the input port. Okay, and then we will also define a lookup table over here. So you could think of this as an array. Okay, so this is the 0th element of the array, the first element, second element, and so on. So this will be our configuration for the 7-segment display. So what are those numbers, right? 3F, 06H, 5BH, and all that. So these are actually the hexadecimal values for the 7-segment display. So remember that to display 0, we would need to light up certain pins. Okay, so certain pins need to be 1 and certain pins need to be 0. And then if we convert these binary values so if we convert these binary values to hexadecimal, based on this table, so 0011 is actually a 3 in hexadecimal. Oops, sorry, this should be a 3. And then 1111 is actually an F. So this 0011 is actually a 3F. Okay, and then for this to display number 1, we will need to have 0000, which is 0, and 0110. So 0110 is actually a 6. So this 8-digit binary over here is actually 06H. So if you look over here, so this is actually the configuration for the 7-segment display for 0, and this 0H is actually the configuration for 1, and this will be 2, and so on. But this thing here actually has some errors, so you will need to check them one by one. So some of the configuration are wrong here, so you need to check them by yourself and see which ones are wrong. And then let's do one more exercise over here. So sorry, 0101 is actually a 5, and 1011 is actually a B. Okay, and this one over here is actually a 0111, a 7, and 0001, 1. So it's actually a 7, 1H. Alright, So this would be our lookup table for the configuration that we will input to the 7-segment display. Now we would set the table address to our data pointer. So dptr is our data pointer, and seg is actually over here, the table, the lookup table that we have. Now let's move on to the start. Okay, so it will first read, so P2 is actually connected to this 8-bit display, 8-bit input, but we will be, if you could see here, we will just be using the first four bits. Okay, so this is not needed. We're just connecting this to our port 2 over here, our input port. So we first read from the P2 to A, and then, so let's say that this pin is on and other pins are off. Okay, so if this is connected, that means that this over here will be 0 because it's connected to ground, you see, okay? And other pins will be 1, so 1, 0, 1, 1, okay? So we actually should read it from the third bit, so it's actually, the input is actually something, 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 because there are no connection over here, and then 1, 1, 0, 1, okay? So this will be the input for port 2, something, something, xxxx, 1, 1, 0, 1. And then this next step over here, A and L, is actually an AND operation. It will mask out the first four, the upper nibble, okay? So 0F is actually equivalent to 0, 0, 0, 0 and 1, 1, 1, 1 in binary, right? So what this operation do is that no matter what is the input for this, it will make them 0, 0, 0, 0, 0, and then it will copy the exact same thing over here. So after this operation, our A will be equals to 0, 0, 0, 0, 1, 1, 0, 1. Okay, so this is another example over here. So let's say that our A input is 1, 0, 1, 0, 0, 0, 0, 1. So let's say after this operation, A and L, A comma 0F, it will do an AND operation. So 1 and 1 will be 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0 and 0, 0, 1 and 0 will be 0, 0 and 0 will be 0, 1 and 0 will be 0. So the AND operation only gives 1 when both of the input are 1, right? So 1 and 1 will give 1. Other cases, it will all be 0. So what it's doing is actually masking out this upper nibble. So these 4 binary over here will be 0, and the lower nibbles will be copied exactly. Okay, so after this operation, the upper nibble, the 4 bits over here will be zeros. Okay, so which is what we get over here. The upper nibble will be 0, and then our inputs still stay the same, 1, 1, 0, 1. And then we'll fit this, move C, so you'll read from the table. So A plus dptr will find from this table the configuration. Okay, so 1101 is actually the 13th element, which is D. So the 13th element, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it will be 5EH. So now our 1 will be 5EH. Okay, 5E hexadecimal. And then we'll move this A, the 5EH, into port 1, which will be connected to our 7-segment display. and it should give a D over here. So it should give out this D. Correction over here, so instead of capital letter D, it should also be a small letter D. Okay, like the B over here. Okay, so I hope you understand what this program is actually doing. And after you reach here, it will jump back to start again. It will read the input and then find from the table again, and then output it to the 7-segment display, and just keep looping over here. Thanks so much for watching. I hope you enjoyed this video. I hope you learned something. And remember to subscribe to my channel, like and comment, and share it with your friends if you find it helpful. And if you'd like to support me, you could go to buymeacoffee.com/dio or paypal.me/dio123. Alright, see you guys in the next video. Bye bye.